into computer says no, and this is the fourth video in my series on stack-based buffer overflow exploitation. So in this video I want to show you how to get started with Mona. We're going to set up a working folder for Mona, so let's go ahead and do that. Down here in the command prompt window, we haven't fired off Mona before, have we? No, we haven't. So you go ! Mona to invoke Mona, and then additional commands are tacked on from there. So we're going to go Mona config and then -set. We want to set a working folder. So I've already created a folder called Mona stuff, and I'm not sure if it'll create a new folder or not. You can figure that out. So this is the command here, and the %p thing is just going to create a new directory under the name of the process that we're running, I guess. So we'll set that up. Hitting enter and waiting. There we go. So the data log should say something about that being okie dokie. Alright, so from here we want to do pattern create. We want to send in that random string, that unique character string, and then we'll use that once we have it. Once we crash the program with the unique character string, we will look at the registers and we'll see what value is in EIP. Then we'll use the pattern offset script to calculate the offset. So it'll compare the entire string to the small portion that's in EIP, figure out the offset, and then we can know how many A bytes to write to the buffer and then into EIP. So you can do PC for short, or pattern create. We'll just do PC. I'm pretty sure behind the scenes this utilizes the same scripts that you've seen in Kali, those Ruby scripts, pattern create and pattern offset. Pardon me. So we'll go pattern create 300 character long string and hit enter. So to give us some feedback here, the string is here in this window, but it does warn us not to use it, to copy it from the file, because characters may have been truncated. So if we head over to Mona stuff, the working folder that we specified previously, we'll see here it has indeed created a folder, and it saved a file called pattern in there with the pattern in a few different formats. We'll copy the ASCII format, close that, minimize that, jump into our script, and we'll send this string over. So you'll see the script is just as it was before. So we'll send that one over, okay, and take a look at it. Just make sure immunity is running, and it is down here in the right hand corner, and we'll hit enter. There you go, we crashed the program. And we see here we have this hex value in here. Let's copy that selection to the clipboard. We can see ESP is pointing to this big buffer of unique strings. We're concerned with this value, and we want to throw it into our little command prompt down here, and we'll do pattern PO for pattern offset, or you could do this. I'll just show you that you can write pattern offset opposed to PO. So yeah, we've copied that value from EIP. We'll hit enter, and it's easy to miss with this small font and everything, and being in red, you might think it's an error, but this is your value here, your offset. So it says pattern 8AE9 was found in cyclic pattern at position 146. So 146, remember that and jot it down. Control F2 to restart our process, and F9 to get it running. So we can get rid of this here, and we now know that the offset is 146, meaning we can send in 146 A's, and the next 4 bytes after that will overwrite EIP, and they will be these 4 B's hopefully. While we're at it, let's send in some C's. It will send in 500 C's to see if we haven't got some room for some shellcode. So we'll clear that. Immunity is running. Yes, indeedy. And we'll fire off the script again. Okay, not times B, plus B. Save that. Plus C. Clear that out. Fire off that script again, and we get a crash. Alright, awesome. As I suspected, EIP has been written over with our B's, as you can see by the hex representation of capital B here, 42, 42, 42, 42. That's great, guys. We now control EIP. We can see the A's are in EBP, and ESP is pointing to somewhere in memory where all of this C, repeating C's lay. So we're going to follow that in the stack. And this isn't very precise, but what you sort of can do is take down this memory address, figure out its numerical value, and sort of subtract it from this address down here to sort of roughly figure out what sort of space we've got. But by the looks of it, that's a pretty big buffer to store our shellcode. Yeah, so this C represents where our not, the C's represent where our not sled and shellcode can be stored. So we know that we can squeeze them in by the looks of it. That's a whole bunch of bytes right there. Not the most elegant way to sort of calculate it, but it actually, it works. You could sit there and count it all if you want, or do that little trick. But by the looks of it, just from experience, that'll be enough. So likewise, that's probably enough for this video, getting on to the 8 or 9 minute mark. In the next one, we'll take a look at generating our shellcode. I think maybe we'll pop a calculator, make sure everything's working well, and then from there we'll probably encode that reverse shellcode, fire up Kali, and have a look at catching a shell over the wire. That'll be pretty cool. Guys, I'll see you in the next one.